So I'm the organizer, so I would like to thank the participant. Okay, so the title is H-versality of Q-Gorenstein deformations and its applications. So later I will explain what's the notion of H-versality. So first let me explain some notion of the Q-Gorenstein smoothing and also some other notions. So when we have some surface, smooth surface, and when we have a -4 curve, then we can contract this -4 curve to the singular point, this basically by Artin's contractibility. Or if you have this singularity, 1/4 1-on type, then also you can do the minimal resolution. So if you have a singular surface, and then you can use minimal resolution, but also if you have some special configuration of this curve, then you can contract to make a singular point. So 1/4 1-on means I'm using this notation. So just action is xy to cx, eta y, eta x, and eta y, and eta is primitive fourth root of unity. So in this case, if we compare with this is x, and then if we compare to this canonical divisor, so then this km is the pi opposite kx minus 1/2 e. So you can see that here is not the integer, so that implies this is, in fact, this is not Cartier divisor, but if you twice, then it goes to the integer. So in this case, 2kx is Cartier. So then this is Cartier divisor. So then locally, this 2kx is isomorphic to OX. So then we can consider the local index 1 cover. So in fact, in this case, local index 1 cover is for this 1/4 1-on singularity is this type, this xy minus g square quotient by xy minus g square. So then this is still singular surface because we have A1 singularity, but it's very easy to give a smoothing, just to give a new parameterized by u, and then here you should be u, and then but in this smoothing we have a Z2 action on this smoothing. So this kind of picture, we have a singular surface with A1 singularity, and then if u is not 0, then we have a smooth surface. But in this total family we have a Z2 action. That quotient gives us in fact the smoothing of this below one. So yeah, here I would like to say that these smoothings are coming from the quotient of this index 1 curve, and it gives us a smoothing, and in fact in this case this is a Q-Gorenstein smoothing. So consider the P2. So now let me explain again more about this Q-Gorenstein smoothing. So consider the P2 embedded by Bernoulli, degree 2, then we embed in P5, and then also embedding P1 cross P1 to P5, and then considering the cone by this V and F in P6. So then considering the hyperplane section through the singular point of the cone is a cone of a rational curve of degree 4. So then if you considering a hyperplane section through singular point, then we have this singular cone, but then if this hyperplane section does not through the singular point, so that gives us, so we have two different smoothing of this CD. One is coming from this V, one is coming from the F. So we have two different smoothing, but if you compute their canonical divisor square, then one direction is the constant, but the other direction we have a jump here. In fact, the general one is 8, but the central fiber is 9. So then this one has some nice smoothing. We say some Q-Gorenstein smoothing, and this is not the Q-Gorenstein smoothing. So previously I just looking at the 1/4 1-on singularity, but this can be generalized to this type of singularity, 1/r squared d, 1 dra minus 1 with GCD equal 1, or rational double point. then this kind of singularity has a nice Q-Gorenstein smoothing. I mean, Q-Gorenstein smoothing I just illustrated by the previous example. So it's smoothing, but with some nice property. So in fact, the definition is that you have a smoothing, and then you have this relative canonical divisor is Q-Cartier. Then we say the Q-Gorenstein smoothing. And then this kind of singularity of these special cyclic quotient singularities are originally studied by Jonathan Wall, because this singularity has some special property if you're considering their minimal resolution graph, and then this self-intersection number is, in this case, is integers. So these are characterized by the self-intersection number is integers. And then much later then, Kolla and Shepard-Barron studied these singularities in the purpose of construction of a compact moduli space of surfaces of general type. So when we try to some compactification of moduli space, we need to allow some singularity, and these singularities are very important in the boundary of the moduli, and they called this singularity of class T. And then there are some important results which use this kind of singularities. One is Manetti used them to construct this famous example of a surface of general type over C to show the deformation equivalence is not same as diffusion peak equivalence. And then Hacking studied also Q-Gorenstein deformations of a semi-low canonical surface over C and used them to construct the compact moduli space of the pairs of a projective plane and plane curve. And then in 2007, I worked with Jong-Il Bak, and then we developed the method of construction of a simply connected or small fundamental group of surfaces of general type over C with PGQ equals 0 by using this Q-Gorenstein smoothings of singular rational surfaces. And then after then, I worked with Nakayama in Kyoto University in LIMS, and then we developed the method with Jong-Il Bak purely in algebraic way. So previously we used many techniques from the complex geometry, but here purely algebraic way, so characteristic free. So then it makes it possible to construct algebraically simply connected surface of general type with the PGQ equals 0 over the field in any characteristics. And then now we are working to developing the more general theory, so it's called the Q-Gorenstein deformation theory over a complete Noetherian local rings. So let me very briefly explain the idea in the previous work. So in 2007, with Jong-Il Bak, we construct the following way. So we consider the P2, and then we choose some very special cubic pencils, and then we blow up these 9 base points. So that makes some special rational elliptic surface, and then we have some very singular fibers. And then blowing up more points over this rational elliptic surface to make some chain of P1, some special chain of P1 to make some singular surface. And then if you just rational blow down of Z, so it means if we changing some tubular neighborhood of this chain of special rational curve to the rational ball, then you can make a symplectic four manifold. So this is originally coming from the idea of the Jong-Il Bak's paper in 2005. And then, but here we wanted to construct the complex surface, not the symplectic four manifold. So then we, using this contractibility, so we contract this special chain of P1 to make some singular point. And then, but we wanted to make some special singularity. So in this case, this singularity of class T. And then, but then I already mentioned that this kind of singularity has a Q-Gorenstein smoothing. So locally, we have some nice smoothing. And then, but this has only locally. So then we need to lifting to globally. So then looking at this spectral sequence from this local and the global X sequence, and then, so for example, looking at this sequence, and then each local smoothings elements of here, and then this represents the first order deformation of the X. So we want to lifting to first order, so it means if we say that this obstruction map from here to here is 0, then we can lift. So then we can, some very special construction, we can prove this H2X equals 0. But this really depends on the very delicately on the constructions. So original box in 2005 construction actually does not work. So in 2007 we modified his original example to work also this. And then one can globalize then these Q-Gorenstein deformations. So this is the very briefly the idea of the constructions. And then in 2011 with Nakayama, and then here we want to construct the same type of surface but in any characteristic, not just over C. So here, but we use the same construction. So construction follows the same idea with the previous paper, except some special characteristics. So for example, if we back to this some special example, but then some special example does not work in characteristic 2 or 35. Then we varying of the examples. So that means here varying the construction depending on the characteristics. So then basically we can construct the all characteristics. So but then if, for example, I explained this kind of singularity, but this singularity does not work in characteristic 2 because if you understand this singularity as a quotient singularity, then we have a problem for characteristic 2. So we have to changing the notion from this special cyclic quotient singularity to changing to special toric singularities. So for example, 1/4 1-on singularity can be understood as this toric singularity, looking at this toric fan. And then these singularities are just coming from the spec of this one, and then this spec is simply the cone of the rational normal curve of degree 4. So this kind of all kind of this special cyclic quotient singularity can be understood as in this case toric singularities. And also one of the main technique to in case over C is that if you're looking at these are the resolutions of the singular surface, then if you're looking at their tangent shift, then actually the push forward of tangent shift of the Z is the same as this on the tangent shift of the X. So, but this works only over C because the injective is always works, but the surjectivity, to prove surjectiveness of this, original proof use exponential map, but this does not work in the positive characteristic. So this does not work in positive characteristic. Also, the other thing does not work in positive characteristic is the tautness. So, if you have something like some resolution graph, over C, this resolution graph determines the singularity, but over positive characteristic, also this is not true, even rational double points. So, over positive characteristic, if you have the same graph of the resolution, but does not determine the singularity. But fortunately, in our old construction, we're using only the spatial configuration, and all configurations are linear chain of P1. So that case actually works. And also this is the example of the imperative characteristic when they are not same. So in characteristic 2, there are two-dimensional families. In the singular surface, you can find the two different derivations, but does not extend to the upstairs. To these resolutions. So characteristic 2 case, this is not, for example, this is not surjective. And then we can solve this all kind of problem by using the toric geometry. So by using this toric geometry, we can solve these problems. But then over C, when we try to prove this simply connectedness, we use a Van Kampen's theorem and also some surgery to prove this simply connected one. But this, Van Kampen's theorem or some kind of surgery does not work in positive characteristic. So over this positive characteristic, we extend the construction over K to this lambda. Here lambda is the complete discrete valuation ring whose fraction field is in characteristic 0. I mean, you can do always this by using, for example, ring of width vectors. So then, using the Grothendieck specialization theorem to apply to this characteristic 0 case, and then if we can prove the simply connected here, then implies the algebraically simply connectedness of the central fibers. So, for example, if you're looking at this kind of pencil over cubics, so originally this pencil over cubics defined over the field over characteristic P in P2, but here all coefficients are integers, so you can extend it to the spec Z. Then you can consider this pencil over cubics and P2 over Q, and then you can extend this result this to the C, and then I mean you can prove the simply connected here, then imply the simply connected here. So that is how to prove the algebraically simply connectedness. But then originally surface is over-defined over the characteristic P. So this surface are defined over field. But when we try to extend to these constructions, so these are not the field, these are complete DVR. So then we need to develop the deformation theory over not just the field, over K, we need to develop some over complete DVR. So that is why we need to develop some Q-Gorenstein deformation theory over lambda. And then we use some Artin's technique of common et al. Neighborhood argument, then we can prove the existence of the smoothings. But yeah, I will explain more about this common et al. Neighborhood argument. Okay, maybe I'm so fast. Okay, let me do slowly. But yeah, I talked many times about this, so hopefully everyone understands the ideas. Okay, so now let me explain by one example to this common et al. Neighborhood. So we have a scheme and we have a point, and that means that we have this spec K to X, and then et al. Neighborhood means that just the et al. Map from here to here, and the Y goes to the X. So this is called the et al. Neighborhood. And then W is common et al. Neighborhood of the two this scheme with this pair. So then if W is et al. Neighborhood of both, this one and this one, then we say the common et al. Neighborhood. So now looking at this example, so S equal this one, quotient by this, so it means now we parameterizing the affine elliptic curve, parameterizing by this S and T, and R is just the central fibers. So we have a affine elliptic curve here, and then we parameterize by S and T. But then in this example, if you for any neighborhood of this from this A2, then we have no isomorphism. But there is a common et al. Neighborhood with these two. So it means that sometimes we have a family, and then you cannot construct directly the map. After some et al., then you can find some map. So that is what I want to say here. So that is, and this is the common definition, and this is one example of a common et al. Neighborhood. Maybe you can understand more clearly when I try to prove some theorem later. Okay, so when we have a complex manifold, then there is a deformation theory. So that there is a deformation of X, means we have X on the central fiber, and we have this family, and this maybe is proper and smooth. So then every tangent vector of this base space, so then if we derivative, that goes to this tangent first order, this H1 of the XTX, and then there is a Kodaira-Spencer map from this tangent space to this T1X, H1XTX, and this map is linear. So this case, this deformation is called complete if every other families, so this is one family, and but you can have other family, then all other families are basically coming from this one, then we say the complete. So here complete, then it means that if you have other family, then you can find some open neighborhood of this point, and then then considering this family, then these families are basically coming from the pullback of this one. Then we say this family is complete. Now this is kind of most important property of the when you have some deformation space or moduli space. Because if you have other family, then basically this moduli space gives the other ones just pullback of this. And then universal means the complete, and this V to B map is unique, then we say the universal. And then Kodaira-Spencer and Kurani's theorem said then there is a complete family such that this Kodaira-Spencer map is isomorphism over analytic space B. But so this is analytic language, and then if we're changing to purely algebraic setting, I mean, these mostly things are done by Grodan-Dieg, Artin, and also others. And then, so when we say the local deformation of X over A, so A is Noetherian local K algebra with the residue field K. So then, so these are kind of, so we have a central fiber, kind of central fiber to this, and so over this A, Noetherian local algebra, we have these flat families. Then we say the local deformations. So then, but some special case, so if this A is Artinian local K algebra case, then this is called infinitesimal deformations. So then, these are, I think, the basic things for, but anyway, I need to just introduce the notion of some basic terminology of this deformation theory. So then we have a covariant functor from deformation X to sending to any Noetherian local K algebra with the residue field local. So then local deformation X over spec A, and then quotient by this divided by isomorphism class. But most cases we are just considering the Artinian local K algebra instead of the total this Noetherian local K algebra. That case is called the functor of infinitesimal deformation of X. So then, so when we have this, try to construct the deformation space, first try to construct this formal deformations. So formal deformation correspond to the construction of the sequence of this over the Artinian local links. So this formal deformation is given by complete local K algebra with the residue field K, and by sequence of this over the family of Artinian local links. And then this formal deformation is called versal. So versal means that if any other formal deformation is reduced by this RS, this homomorphism from R to S, and they are coming this. So it's some kind of a similar notion of the complete in the complete analytic setting, but here formal deformations. And the minimal means the versal plus this, we have a unique homomorphism from this tangent space. So then it's called minimal. And the pro-representable Hall means the versal plus minimal, then it's called the pro-representable Hall.
Why minimal and not universal?
Some paper has said minimal, some yes, miniversal, yes.
Universal, minimal, okay.
Yes, also semi-versal, but actually most cases we follow the Artin's notions. So, but other people use some, especially analytic category people use something different notions. But here we're using minimal. Okay. But it's same meaning as a miniversal, yeah. So, but that is then pro-representable Hall. And the universal means the versal plus this is unique. So these are the language of the almost the same language for the analytic setting, but in the view of the now a purely algebraic setting. And here these are all related with the formal deformations. And then Schlesinger limb give us some condition for pro-representable Hall. Actually, in many interesting cases, I mean, this pro-representable Hall works for many interesting cases. So, for example, this deformation X, this functor satisfies the Schlesinger limb condition if X is proper over K and X is affine over K with only isolated singularities, or X is spec over local ring over algebraic K scheme at an isolated singular point. But previously, I said there is formal deformations, but the formal deformation, when we construct formal deformation, then it does not necessarily this is scheme. So there is some example which is a formal deformation, but this X does not represent by scheme. So if this is represented by scheme, then we call the effective. And the algebraizable means but effective also still does not enough when we try to construct some smooth surface from the singular one, because then we need element from this fiber. But effective is only for the local link. So if we try to construct the smooth one, we need the algebraizable. So this is algebraizable means this formal deformation is induced from the algebraic deformations. So that means these are coming from some scheme of families, and this local link at the point is the original, same as the original one. So then we say the algebraic deformation. So then we can say what's the general fiber or also others. And this kind of all theory is basically developed by Claude and Diego Attin, and they give some criterion for algebraizability. And then, in fact, previously I said that this kind of arguments for over K, but all arguments can be generalized to complete local link with the rigid field K. So then we can change into this deformation functor from category of Noetherian local lambda algebra and the category of Attinian local lambda algebras. So then after then, so now we have, for example, now we have an algebraic deformation. Then, but also we want to say similar notion of the completeness. So now let's theta be an algebraic deformation of X over a scheme T. Then this theta is H-versal, this H coming from the Henselizations. So that means that if this A to spec R and A prime to spec R, so then when we have A to this map from A to theta, that it can be extending from A prime to theta. And here R prime R to a surjective local homomorphism of Henselization of local lambda algebras. So maybe it's better to understand by this remark. So if theta satisfies H-versal, so we have this algebraic deformation, and if this algebraic deformation satisfies H-versal, then for any object theta prime of deformation of this lambda scheme of T prime for any object, then after eta labeled, then we can extend it. We can have this morphism from this family to here, this original H-versal family. So it means that any algebraic deformation of X is a pullback of the H-versal deformation up to eta equivalence. So this I already gave one example in the previous this when I explained the common eta labeled. So maybe let me back on. So here. So we cannot find directly the eta labeled, but after common eta, so common eta means that after some eta, then you can find the map. Okay, so then so this is the very important property for H-versal, and this is exactly the notion of the complete in the analytic setting in this algebraic deformation case. And then Attin gave us some criterion for H-versalities for these deformations. But then when he tried to prove this H-versality, he did not use directly the deformation functor. So maybe this kind of similar thing happening when you try to prove some directly on the moduli space. You have some difficulty, then you go to some step. So here he also using some 5th category in groupoid instead of the deformation functors. So what's the 5th category in groupoid? So 5th category in groupoid means the functor between two categories from F to C. So satisfy this property. So 5th category in groupoid over C if when you have so usually in the deformation, so this base space. And these are the family. So when you have B to A and when you have family over A, then you can find Y. This is, I mean, in practical example, you can find this Y, just the direct product. And then the second one is related to some kind of isomorphism. So when you have object in this base space, and if you have two family over here, and they have a map from the same X, and then if you have a morphism over the base space, then you have a unique map from Y prime to Y. So this is the second condition. So then co-fibred category is simply the opposite object of the fibered category in groupoid. Because sometimes we need to consider so when we consider deformation, we consider the family over scheme, but if we changing to the language of the links, then the direction is reverse. That is why sometimes we need to introduce the co-fibered categories. So then, for example, this flat lambda morphisms, YT, so FL lambda means the category of flat lambda morphisms, and the scheme lambda is the category of Noetherian lambda schemes. Then we have the fibered category in groupoids, just forgetting this Y. And then also we can consider the category of objects in FL lambda under X spec K. So we fix this scheme XK because in general, I mean, when we consider deformation space, then we first fix X, right? So then we consider the family of X. So that is the why here FLX is just fix one X, and then considering this flat lambda morphisms, category of flat lambda morphism, that is called FLX. And FPX is the full subcategory of the FLX for only considering the proper K schemes. And then also we can consider when X is a affine scheme over K with the isolated singularities. So then we also consider the fibered category in groupoid of a scheme lambda is called Fi sol X. But here morphism is we have to consider the morphism after ethyl equivalence. So then Grodendieck and Artins proved if X is projective scheme over K, and if this is the formal scheme, proper morphism of the formal schemes associated with the minimal versal formal deformation of X. And if there is a relatively ample invertible sheaf on the formal scheme, or H2X equals 0, because if this equals 0, then you can extend these line bundles. So then this FPX means H-versal algebraic deformations.
So that's an O, H2O. Right?
Yes, H2O, yes. Okay. Yes, H2OXOX. Yes, yeah, thank you. And then also the singular case, so Artin also proved the X is equidimensional affine algebraic scheme over K with only isolated singularities. So then this Fi sol X also means minimal H-versal algebraic deformations. Now let me illustrate one theorem in our previous paper with Nakayama. So X is Q-Gorenstein normal projective variety over K with isolated singularities. And suppose any singular point is Q-Gorenstein smoothable and H2X OX equals 0. And the third one is one of the following three conditions. Kx is ample or minus Kx is ample. Sorry, this is not OX. This is TX, sorry. TX, yeah, because here, yeah, this is, yeah, sometimes I use theta x, but this is, so theta x or tx, okay. So tangent, h of tangent sheaf equals 0. Then x means Q-Gorenstein smoothing over k. Okay, so let me illustrate this proof by using the previously this deformation functor or this fibered category is something like FPX is minimal H-versal or common ethyl labeled argument. Sorry. Okay, so now choose P equals singular point X. So then each singular point, we know that this deformation X, this singular point, is algebraizable and pro-representable whole. So, and also we assumed any singular point is Q-Gorenstein smoothable. So this means that we have a family over this singular point, and also we have from this algebraic the pressure representable Hall. So it means that these are coming from the first condition. Then after some replacing by at the level of the P, then we have a morphism, because this deformation of this one algebraic and pressure representable Hall. So we have some morphism from this construct first condition to here. So then, but also we know that this total deformation X is also algebraic and pro-representable Hall. So it means that we have also this algebraic pro-representable Hall for X. So then, but then this total deformation to each singular deformation of each singular point, but this also algebraic pro-representable Hall, both are pro-representable Hall. So it means that after at that neighborhood, then we can have a morphism from S to this each TP, this product of each P. So then second condition is this H2X Tx equals 0. So that implies the you can lifting. So it means that after replacing also by at that neighborhood, then there is a morphism from this Q to S. So then just the product, this WQ2 over S, so then that's satisfying Q-Gorenstein smoothing. But here we have to a little bit, there is a technical thing, is checking some Q-Gorenstein properties are preserving by this. Then we can say this gives Q-Gorenstein smoothing. So it means that if this kind of functor, deformation functor is some pro-representable or algebraic or H-versal, some nice property, then you can some kind of formal argument give us the proof of this kind of theorems. Okay, so then now I would like to define what is the Q-Gorenstein, these deformations, and the Q-Gorenstein morphism, because to defining the so when I say the deformation functor or 5-ring category of this FPX or F isol X, but this Q-Gorenstein smoothing is not the full of the deformation. We have to consider some special deformation. So we need to define this Q-Gorenstein smoothing or Q-Gorenstein morphism and the Q-Gorenstein family. So that is why here we need to define the Q-Gorenstein scheme and the Q-Gorenstein morphisms. So let me define what is the Q-Gorenstein scheme of D. So X is Q-Gorenstein scheme of dimension D means that if X admits a dualizing complex locally, and the second condition is Gorenstein in codimension 1, and this HDR star from the complex is invertible on the Gorenstein locus, and this is invertible for some R. So these are related with the Q-Gorenstein. And here we define as much as general, so to include the isolated singularity, but also we want to include some codimension 1 singularity, but some nice case, something like normal crossing case. So this is why we rather general, our definition is rather general. And then, but this kind of a condition satisfy in many cases. So for example, let's see, if X is algebraic scheme of a field, then always this dualizing complex exists, because if you have a morphism from Y to T, and if T admits a dualizing complex, then upstairs also admits a dualizing complex. So spec A has a dualizing complex, so this also has a dualizing complex. And also Q-Gorenstein scheme satisfied this S2 condition, set S2 condition, and the push forward of the structure shift is of the Gorenstein locus is the OX. And but if you give a Cohen-Macaulay condition, then this dualizing complex is simply the shift of the dualizing shift, And if X is Gorenstein case is the usual definition, same as the usual definition, Rkx is Cartier. And then what is the Q-Gorenstein morphism? So if Yt is flat morphism and Y0 is relative Gorenstein locus, and this is relative dualizing sheaf, and this is Q-Gorenstein morphism if the codimension is of this nice locus, I mean, just bad locus is codimension is greater or equal to 2 for any these fibers, and then this is the definition of the push forward of this nice locus to coherent on Y and flat over T, and each this fiber of this relative dualizing sheaf tensor K is satisfy S2, and this is also invertible for some R, then we say this is Q-Gorenstein morphism. So then this Q-Gorenstein morphism, if you have a Q-Gorenstein morphism, then this bad locus codimension is greater or equal to 2, and each fiber is Q-Gorenstein, and if this T is Q-Gorenstein, then also Y is Q-Gorenstein, and this is one important condition. So total is this M is invertible, then each one is invertible. And then also this Q-Gorenstein morphism definition works for the base change, and then also works for the when you composite of the maps, and then Q-Gorenstein morphism is also local conditions, and then also you can check the Q-Gorenstein with just the checking by Artinian neighborhood.
Sorry,
Okay. Let me go. Okay, so then now we can. Yes. Pardon? So these are Q-Gorenstein morphisms, and this definition of Q-Gorenstein schemes.
Because this was this condition that is taking the reflexive tensor product combination.
Yes, something like right.
This is the Kolar condition.
Yes, that is one of Kolar's condition. That is.
It's automatical because you require that the base is Q-Gorenstein.
Oh no! We do not assume the base is. Actually, our definition is more general than Kolar's definitions. Yes. In Kolar, always assume the Cohen-Macaulay, but we do not assume the Cohen-Macaulays. Actually, that condition is related much about the Cohen-Macaulay conditions, but we do not assume the Cohen-Macaulays. So then we can prove that if X is Q-Gorenstein projective scheme over K, and if H2X OX equals 0, or this tensor M is ample, then this FPX QG. So previously I defined this 5th category in FPX, but here QG means only considering the Q-Gorenstein morphism. So then it means also minimal H-versal Q-Gorenstein deformations. And also if X is affine algebraic Q-Gorenstein scheme over K with isolated singularity, then also when we consider only QG for F isol X, then also it means minimal H-versal Q-Gorenstein algebraic deformations. So proofs actually we follow the Artin's argument of when Artin proved this usual this without QG, this FPX is H-versal, minimal H-versal, and F isol is minimal this H-versal. But yeah, we followed, but there are many technical things to prove this. So because of we have to check every argument of his one to satisfy this kind of with the Q-Gorenstein conditions. Sorry. Yeah. Yeah, okay. So then there are some previous study about this kind of Q-Gorenstein deformation. So Hacking studied this Q-Gorenstein deformation. So he considered this deformation functor, but with the QG when X is a semi-low canonical surface, when this field is characteristic 0. But he used the index 1 cover. But index 1 cover is very good technique when you consider characteristic 0. But one problem is that this only defined as locally, because the index 1 cover is basically coming from the some R times of Kx is Cartier. So then locally you have only local equations. So problem is then when you construct, then only you can construct as not scheme as some kind of stacks. So then he used kind of canonical covering stack and G equivalent shift by using the Illugi's result. And then also Nikos, he considered the X is a Cohen-Macaulay case and Gorenstein in codimension 1 surface over K, but he also considered characteristic K equals 0 because he also used the index 1 curve. But he also studied more this cotangent complex. So actually our case still we do not consider this obstruction map, but he a little bit considered this obstruction map. So this is why he considered cotangent complex. And then he proved this deformation XQG is pro-representable and algebraizable in this case. But no one touched this Q-Gorenstein things H-versality. And then one important corollary is that if we're using this theorem, this H-versality, then we can simplify the previous proof. Directly, we can use this PXQG's H-versality of this one. So this is another application of this functor is H-versality. So now a surface singularity is a toric singularity of class T if it is a singularity of the toric surface of this coming from this toric surface. So in C, these singularity are simply this special cyclic quotient singularity, 1 over dn square, 1 dna minus 1. So Kolla and Shepard-Barron called this is a singularity of class T. But here we want to do field of any characteristic, so we just generalize this definition to toric, so toric singularity of class T. And then we can prove this characterization of this kind of singularity. So let X be a germ of normal surface singularity defined over K, and if this is rational double point or toric singularity of class T, that is the equivalent to this admits especially Q-Gorenstein smoothing, and this is log terminal in the usual sense. And then XQ is QICI, means that this Q is coming from the X is Q-Gorenstein, and I means the index 1 cover over an eta neighborhood is a normal surface with isolated complete intersection singularity. So this is why we define this, because when you consider the over C, if you consider this singularity, and then if you consider index 1 curve, is simply the rational double point. So that is the complete intersection singularity. So that is the reason why we define QICI here. Because this here is more special than rational double point. Because we do not consider the TN type and the EN type, only consider the AN type of the rational double point. I mean, in this.
What does it mean, index 1 for?
Oh, because the Q-Gorensteins are related, we have some R times is Cartier, so that coming from this index 1 couple.
But index 1 is more, no, you don't understand.
Index 1 is it depends on so index 1 cover is coming from the RKX is locally isomorphic to OX. But these depend on this isomorphism map. So if you're choosing different isomorphism map, then index 1 cover maybe change it. But it may be characteristic over C is okay, but characteristic P, this is not same. So it depends on the isomorphism. Okay, so then let me give a proof of this using this H-versality of the Q-Gorenstein deformation functors. So let me prove not this direction. I will just prove these directions. So now let me explain the idea of the proof of this direction. So here we wanted to prove this, that if we satisfy this, then we want to prove rational double point or toric singularity. But if you assume X is Gorenstein, then very easy to prove this rational double point. So here we do not, so now we assume X is not Gorenstein. So then considering the minimal resolution, this minimal resolution, and then let lambda be a complete DVR of a mixed characteristic with the residue field with K. So, I mean, you can choose, for example, ring of Witt vectors. So then there is equisingular deformations yt of X over this smooth lambda scheme T. So equisingular deformation. And then we can prove, in fact, this equisingular deformation satisfies Q-Gorenstein morphism. And then we know the F-isol X, QG, admits H-versal algebraic Q-Gorenstein deformation. So it means that now this YT here, so these are coming from the equisingular, and we know that this is H-versal. So we have this coming from this H-versality, we have this ZS. But then the property of H-versality said, after eta neighborhood, then you have a morphism from here to here. So this from equisingular deformation, after some eta neighborhood, then you can send this here to this Q-Gorenstein deformations. So then now we have this diagram. So these are just eta covering here. And then we have this Z to S. These are coming from this H-versality and this equisingular. And now this everything is over-defined over this spec lambda. So then over spec lambda, special point is the original spec K, but the general point is the defined over characteristic 0. So now we are considering the eta is point of T prime lying over the generic point of the spec lambda. But we know that this general over general point, then this characteristic 0, these are just to make a geometric fiber, to making algebraic closure. So then now we have this fiber over the generic point, geometric fiber. And then now we have a spec K to T prime, so these are coming from geometric fiber. And then now say the sigma equal G eta coming from here. So then geometric fiber, this Z bar over ZS, here this geometric fiber is isomorphic to geometric fiber over here because of this, right? Because you just choosing here and this is just pullback of that. So we have a isomorphic of geometric fibers. And then dual graph of the exceptional divisors of the minimal resolution of the Y bar coincide with the that of X, since this is coming from the equisingular, because these are equisingular, so your exceptional divisor of central fiber is the same as special fiber is the same as generic fiber. So then singularity of Y bar and the Z bar are eta equivalent, we know this. So then that eta equivalent implies the dual graph of the exceptional divisors of the minimal resolution of Z bar coincide with that of X. And the Z bar also admits Q-Gorenstein smoothing because the Z is coming from this F-isol and these are coming from the Q-Gorenstein. We know that this singularity we assume that this is Q-Gorenstein smoothing. So then by using the result in characteristic 0 for Z bar, then this one should be toric singularity of class T. So basically, if we apply to this H-versality of the Q-Gorenstein deformation functor, and then if we can prove equisingular deformation is Q-Gorenstein morphism, and then we can just apply the result in characteristic 0 to characteristic P. So then finally we can characterize this theorem. So this is one maybe application of also the H-versality of this Q-Gorenstein deformation functors. Yeah, let me stop.